A radioactive isotope which is used in diagnostic imaging has a half-life of 6.0 hours. If a quantity of this isotope has an activity of 150 microcuries when delivered to a hospital, how much activity will remain 24 hours after delivery? Alright, now this question is on radioactivity. In as much as it's on radioactivity, it's also on first order reactions. It's on chemical kinetics. Why? Because majority of radioactive decays, if not all, are always first order reaction. And if you are given a question like this, if they are silent on the order of the reaction, right, just know that it is what? First order. If it is not first order, they will state it. They will let you know that this reaction is either second order or zero order, as the case may be. So since they are silent on the order of reaction here, it means that the reaction is what? First order. So what are we given here? We are given the half-life of this radioactive isotope. We are given the activity, the original what? Activity of the radioisotope, and we are given the time. We are given the time t and asked to determine the concentration or the activity that will remain after time what? T, which is 24 hours, right? So let's write out our parameters. We have half-life. The half-life given to us here is T half. That's 6 hours. 6 hours. You can as well convert it to seconds, which will be 6. It's not completely converted to seconds anyway. You can leave it as this, which is 6 hours times 60 minutes over 1 hour times 60 seconds over 1 minute. So this will go, and then this will also what? Go, leaving with us with what? 6 times 300 and 3600 seconds. It was 21,600 seconds. Okay, what else are we given here? We are given the activity. Okay, let's call that let's call initial, or call it original activity. That's 80. That is 150 microcuries. So we have to convert this to standard units, which is micro is 10 times 10 is power minus 6 curies. So this will give us 1.5 times 10 raised to power minus 4 curies. Okay, then we are given the time. We are given the time here, time 24 hours. We are given the time of decay. That's T to be 24 what? Hours. And we can convert this to seconds. By multiplying by 3,600 seconds all over 1 hour. So that gives us 86,400 seconds. Okay, so next year, what are we meant to do? We are now meant to find what? The activity. So final activity. Oh, sorry, this should be A naught, not 80. That's the original activity. Final activity, that's 80. Activity at time T is what we are looking for. So applying the first order reaction, the first order equation of reaction, we will have natural log of AT equals to natural log of A naught minus KT, where K here is the decay constant and it's calculated as 0.693 all over what? Half-life, or ln 2 all over half-life. Okay, so from here, what's the half-life? Our half-life here is 21,600 seconds. So if we substitute that into this, all over 21,600 seconds, the value of our K will be 3.208 times 10 raised to the power minus 5 per second. Okay, that's ln AT equals to a natural log of 1.5 times 10 raised to the power minus 4 curie minus, okay, our rate constant, decay constant here, 3.208 times 10 raised to the power minus 5 into, what's the time? 86,400 seconds. 86,400 seconds. This per second, by the way. Okay, so this will give us minus 8.805 minus, if we evaluate this, we get 2.772. so this will give us minus 11.576. okay, but that's not the final answer. You're looking for the final activity after 24 hours. So from here now, if we evaluate this, this will be AT equals to exponential minus 11.576. So evaluate this, that will give us 9.39 times 10 raised to the power minus 6 curies, which is less than the original concentration or the original activity of the radioisotope. The original activity of the isotope was 1.5 times 10 raised to the power minus 4 curies, and after that we had 9.9 times 10 raised to the power minus 6 curies, which means we are correct. Since the question gave us the activity in microcuries, then we must also present our answers in microcuries. This will be 9.39 microcuries, because 10 raised to the power minus 6 is micro, right? So that's micro, which is less than the original activity, which was 150 microcuries. So that's the activity that will remain after 24 hours. Alternatively, you can use the differential equation. That's AT over A naught equals to exponential minus KT, right? So which means that here AT will be equal to A naught exponential minus what? KT. If we substitute the values, that will be, what's that A naught here? Original concentration here is what? 1.5 times 10 raised to the power minus 4. That will be 1.5 times 10 raised to the power minus 4 is exponential raised to the power, was a order of reaction here, 3.28 minus 3.208 times 10 raised to the power minus 5, right, per second, times our time, 86,400 seconds, times 86,400 seconds, which is 1.5 times 10 raised to the power minus 4 curies exponential minus 2.772. Right? By time you evaluate this, will be 1.5 times 10 raised to the power minus 4 curies times 0.06254 gives us 9.38 times 10 raised to the power minus 6 curie, which is the same thing as 9 or approximately 9.38 microcurie.
So if this video was helpful to you, drop a comment and hit the like button. Also, if this is your first time here, subscribe to our channel and turn on your notification bell to always stay updated with our new uploads. Always strive to be a better version of yourself until I see you when I'll see you.